Okay, no one has joined. Let's wait for 5 minutes. Let's wait for 5 minutes. Okay, so let's begin. Uh, Now, before I begin the class, though there is no one, let me just announce if there is a any connectivity issue or if I get disconnected, please wait in the same link, right? Because I'm currently taking this lecture outside my usual place, so there might be internet connectivity issue, right? So, in case of disconnection, please wait. Let's see. So just in case if anybody joins later, this message is for you. Okay. Yeah. So let me start today's class. So welcome everyone. Good evening. So we are in week 10 of this live interaction session, where every Tuesday we meet for problem solving session for this course, which is Matlab based programming lab in chemical engineering. A brief about me: I'm Bhavesh Moorjani. I have completed my bachelor's from MS University Vadodara, where I was introduced to this Matlab course, and after that I joined IIT Bombay as a PhD student, and in my PhD work I use Matlab here and there for various analysis part, right? So that's why I have selected this course to help you guys with to get familiarize yourself with Matlab, so that you can solve various problems in the Matlab, right? So till now, from week 1 to this is 10th week, right? So every week we have discussed some new topic or some problem. So we started with the basics of Matlab, basics of programming, where we learned various fundamental commands that has been used in the Matlab, various fundamentals of programming, various loops. Then after that we started with the specific problem of chemical engineering in Matlab, right? So from week 3 onwards we started solving various problems of chemical engineering in the Matlab, where our approach was first to understand what are the numerical methods that we are using, and after that we tried to code that problem into Matlab programming, right, through the numerical method, as well as we have used inbuilt Matlab commands to solve the problem. Now currently the type of problem we are solving involves the partial differential equation, right? So if you recall the previous lecture where we solved the problem of reaction in the catalytic palette, right, where diffusion and reaction both were happening, so that was a partial differential equation domain problem, right? Similarly, previously we also solved two-dimensional heat transfer problem for a fin, which also involved partial differential equation, where we solved numerically what will be the temperature profile in that fin for various time instant and the location, right? So we computed the spatio-temporal profile, right? So these are the equations. I hope you have seen it and coded it, right? Similarly, the problem that I have solved in the last lecture, right, which was of heat transfer through this fin, where we employed the numerical methods, we solved it via numerical method. Sir has done same problem in 10th week lectures, right, where you have been given this two-dimensional plate, right, for which various boundary conditions are given, although the time parameter is not here, but still it's a partial differential equation since you have two variable x and y, right? And then you have to solve what is the temperature distribution profile across this path, right? And this for that you rely on the PDE model solver, which is inbuilt in the Matlab. So what I will do in today's class is that I will start with the concept of partial differential equations, what are the numerical methods available for solving the PDEs, what are the characterization of PDEs, and then after that we will solve PDEs with the help of Matlab toolbox and inbuilt commands, right? So this is the strategies for today's class. Okay, coming to the partial differential equations. So when I say partial differential equation, what strikes in your mind, that these are the equation which involves a function which is a multivariable, right? Multivariable meaning more than one variable dependent function, and the equation involves that function and its partial derivative with respect to those variable, right? So if function involves more than one partial derivative of a particular function, then it becomes partial differential equation. Now in comparison to ordinary differential equations, which we have been looked at over, if you go beyond last 2 lectures, right? So there we were looking at ordinary differential equations, where we solved ODE initial value problems, ODE boundary value problems, right? So that generally involved only one independent variable. So generally it was time, where we mostly studied the reaction engineering problem, right? So reaction in the plug flow reactor, CSTR reactor, etc. But now in that part we had only one variable which was acting as independent, generally time, right? But in partial differential equations you have 2 or more variables which are independent, right? So your function is varying with more than 2, minimum of 2, and it can go more than 2 variables, right? So in that case you have multiple differential equations present in your system, multiple differentiation of your function with respect to different independent variables. So general form of a PDE, you can write it in this fashion, right? So if your function is u, right, which will be dependent on more than 2 variables, right? So let's say x and y are minimum 2 variables. Beyond that you can have multivariable. This is your function u, and then you could have the first derivative of your function with respect to x and y. You could have second derivative of your function with x and y, and so on. So generally we deal with the second order partial differential equations only, right? So let's say u is an unknown function, then derivative of u with respect to your independent variable x, it will be referred as first partial derivative of u with respect to x. Similarly with y, and then you have second derivative, right? So this is the general form, right? Now so this is the characterization of PD. Now within the PD also, what are the examples as an engineer that we deal with? So if you recall the last lecture again, so there we solved the 2D heat transfer problem, right? Where we had differentiation of temperature on the left hand side, and on the right hand side we had the spatio profile of your temperature, right? So k times del square T by del x square plus del square T by del y square, right? So this comes from your Fourier's law, the translation of Fourier's law in the higher dimensions, right? So in that case you get this spatio-temporal profile, which describes your change, how your change in temperature works with time across both position as well as time, right? So instead of you can consider it as T. So T will be your, that will be your temperature at different position and time, right? Then if you work with fluid dynamics or fluid mechanics, or in that case you will deal with the wave functions, right? So that you have this wave equation which involves both temperature and the space derivative, second order derivative of your function with respect to temperature and the space, right? So generally the propagation of wave is determined by this equation. Then you have Laplace equations. So Laplace equations are generally used to describe the steady state conditions or equilibrium conditions. So right, so many a time you will come across this equation. If you recall all your fluid flow transport phenomena part, this kind of profile, this kind of equation you write it. So these are the Laplace equations. So in all this, what is common, that you have one function u, right, which is dependent on more than 2 variables. More than one variable, so 2 or higher, right? And then you have your functional form or the equation which is written in the form of the partial derivative of u with respect to this independent variables, right? So that becomes your example of PD. Now if you want to characterize this partial differential equation, that if I have a partial differential equation, what kind of category I can put it in, right? So as a engineer, we deal with the mostly you will deal with the second order partial differential equations, right? With generally two variable. So here we have considered the example of that, and you can write this your PD with respect to two independent variables. So you have your second order derivative of your function. You have second order derivative of your function with respect to only first variable, with respect to both variable, and with respect to only second variable, and then rest of the term. So here you will have the first order partial derivative and the normal values, right? If you only focus on the second order derivative coefficients, so a, b and c here, based on the value of b square minus 4ac, you can determine what kind of partial differential equation you have. So if your b square minus 4ac becomes 0, that means you have a parabolic equation. If your b square minus 4ac is 0, that will be hyperbolic, and b square minus 4ac, it becomes elliptical. Now, why this classification is important? So based on this classification, you can determine the way your system will behave, right? So in the parabolic heat equation, if you will look at the parabola, the way it evolves, at the end it goes and attains to a steady state, right? Kind of a exponential equation. If the way exponential equation attains the equilibrium value at the end, similarly parabola at the end will also attain an equilibrium value. So generally that shows the steady state in your heat transfer part. Now if you compare this with the heat equation we have seen previously here, right? So I have to look at the coefficient of the second order derivatives, right? Second order derivatives. So here I only have one coefficient, which is alpha, right? So if I put it in this case, let's say b square is 0, because I don't have any second order derivative with both variables, right? Let's consider it as a. Your c is 0, so your b square minus 4ac becomes 0, so your equation becomes parabolic. Then for the hyperbolic part, we have wave equation. So here you have both the coefficient. So one coefficient is 1 and second coefficient is c square. B value is 0, so that becomes 0 minus 4 c square, right? So minus 4 c square, I think it should be minus 4 c square. Sorry, this is not, this won't be plus c square, it will be minus c square, because you have to put all the equations in the one side, right? So one coefficient will be 1 and second will be minus c square. So 0 minus 4 into 1 into minus c square, so that will become 4 times c square, which is greater than 0, right? So that becomes your hyperbolic equation. And for the elliptical part, so the Laplace equation, both the coefficients a and c are 1, b is 0, so that becomes 0 minus 4, which is less than 0, so that becomes elliptical. Now this equation will dictate the manner your system will evolve, what kind of initial condition and boundary condition you will need, right? So coming to the boundary condition part. So for the ordinary differential equation, since we have differentiation with respect to only one variable, so there we start with some initial condition, and the way this solver, the ODE solver or the numerical method, the Euler method and RK method that we have seen previously, the way it works is that you move ahead in that variable, and based on the previous value of that variable you compute the next value, right? So you move ahead with the increment. So for that you need some initial value. So most of the ODE you had seen were the initial condition problems, right? But most of the ODEs were the initial condition problem, and there were some boundary condition problem also, to which we saw the solution method, that since you need some initial value to start with, so either you can use a shooting method, or you can use a scaling method. So in that case, you can use a shooting method, and in that case you will have the initial condition problem, right? So where you guess some initial value and move ahead with the time, and at the end confirm that the guess value is it leading to the other boundary condition or not, right? So that was shooting method in ODE boundary condition problem. And then second was that you use the discretization part and you call specific ODE boundary condition solvers, right? So that BVP4C and BVP5C, which were the ODE boundary condition solvers where you discretize the problem and solve the simultaneous equations, right? Then but when we are talking about the partial differential equation, so here since we have multivariable functions, right? So u is dependent in x and y. So here it could be temperature dependent, it could be your space dependent also. So you might end up with both initial condition as well as boundary condition depending upon what kind of equations you have, right? So here for ODE you will have both initial condition as well as boundary condition. Initial condition will specify what is your starting point in your equation, right? So generally all the PDs which involves time, you will have some initial condition, right? And then boundary condition, obviously it will give you the extreme boundary values. Now here also there is this further differentiation in the boundary condition. If your boundary condition only involves your function value, right? So if your boundary condition is written in terms of the fixed value of your function, it becomes direct boundary condition. But if your boundary condition is in terms of the derivative of your function, let's say du by dx in this case, in that case it's called as Newman boundary condition, right? So these are the two differentiations. So these general terms are used, and if you will see, if you have followed the search lecture and tried to use that PD modular part, in that also you will see when you change the boundary condition, when you want to put the boundary conditions for your partial differential equations, you get this two part, right? Either this direct boundary condition or the Newman boundary condition. Okay, now why this boundary condition becomes important for partial differential equations is that if you will see PD alone, since it's a multivariable problem, right? If I want to solve it, I will have an infinite solution because there are multi-variables. You can change one variable, keep other variable constant, and land up with some values, right? So for that, to get a unique solution, you have to have some initial condition and boundary conditions to find that unique solution, right? So when you are given the PD problems, you also need to know what are the initial conditions and boundary conditions to solve this problem. Now approach for us to solve this PDs, so there are three approach, like three way that we can use it, essentially actually two ways. So one is the analytical solution and the second is the numerical solution, right? And third is a Matlab route, which is obviously part of a numerical solution. So in the analytical solution, you try to solve this partial differential equation analytically, right? Where you employ your this variable separation method of characterization, or some integral transform where you use Fourier or Laplace transform to solve them analytically, right? The variable separation method, I think it's a very common method. You might have seen in your 11th-12th standard also, right? So these are generally good when you have a lower order or low variable problems involved, and where you can easily separate your variables, right? Then only you can use it. So although they provide you exact and general solution, right? But when your system becomes too complex, these methods are not easy to incorporate, right? So you cannot get always the analytical solution. That's why we rely on the numerical solution part. And in the numerical solution, the core idea is that you divide your system into multiple discrete continuous part, and then convert your system into various system of equations for various discrete points, right? And then you solve this equation simultaneously. So there are three common methods that has been used. One is FDM, second FEM, and FVM. What are these methods, right? So first FDM, that refers to finite difference method. So what you do, you discretize your system into multiple points, and then you approximate the derivatives using difference quotation, right? So generally all the numerical differential equations that we have seen, your central difference method, forward difference method, they fall under this category. So here I think it was shown. So by discretization, what you do is you divide your system into multiple grid points, right? Now once you have this grid point, for each data point you write your system's equation. Okay, now here generally what happens, since you have your function is partial differential equations, you have this derivatives. Now to compute the derivatives at various points, you rely on the numerical method, which is a forward difference method, central difference method, or backwards difference method, whatever you want to use. That's why it's a finite difference method, right? So you rely on that, you compute the derivative, be it be first order derivative or the second order derivative. You compute the derivative, and then you can put this derivative in your main primary equation, right? Then this primary equation becomes a system of primary equation becomes part of some unknown variables, right? Then you have multiple such equations ready with you, then you have to just solve them simultaneously, and then you will get the solution, right? So that is the core idea behind finite difference method. Similarly, or the numerical method, any all the other methods here also, okay? So if you search, if I just look at the finite difference method, by the way, the finite difference method we already solved in the last class, right? So if I show you the previous class note, is it open? Yeah. So this problem of heat transfer through fins, right? So here we had this second order derivative, and we tried to solve this numerically. So for the second order derivative, we relied on the central difference method to find this derivative, right? So basically this is nothing but a central difference method, finite difference method that we have used. So in finite difference method, with the help of Taylor's polynomial, you define derivatives, first order and second order derivative with respect to the functional value at the corresponding plus or minus delta h point, right? So these are the equations that we have used. This was the second order differentiation equation, right? Then comes the finite element method. So for the finite element method, here also the concept is similar, that you divide your system into multiple grid points. But unlike your finite difference method, where you divide your system into fixed width, so in the previous case, in the rectangular fin case, we moved at every delta h, right? So you select the delta h in x and y, and then you create this grid, so that width is fixed, so your points are also fixed, right? But in the finite element method, the grid that you divide is generally different. So it involves some complex geometry, right? Based on that, you divide your system into multiple grids, and then use various set of equations to solve your system's equation at this point, right? Now here I'm not going into the details, because this concept is also new to me, and it's not needed as of now for us also. But this is how the finite element and the finite difference method differ. Similarly, you have finite volume method. And so here also the description is given, and along with the equation part, right? So the common idea in all this method is that you start with one, so you discretize your system, in multiple points, and then solve equations of your system at this points, right? So with this you can handle the complex problems, real world problems, which are generally of higher order, right? But the cons is solution is approximate, and then depending upon the accuracy you want and kind of problem you are solving, you might require a higher computational power for this problem. So what we have done in the last class, if I open you the previous code, week 9 tutorial, right? Or let me just show you it today again. So what we had done in the last class was we used finite difference method. We use this finite difference method to solve our rectangular fin problem, right? Now there are inbuilt Matlab tools which you can use to solve these PD problems. So there are basically two primary workflow that has been given in the Matlab. First is PDPE solver, which is a one-dimensional parabolic and elliptical partial differential equation solvers, right? So what it does, it involves your one time derivative and one spatial derivative, right? So if you recall the last class, in the last class only, the reaction diffusion problem, we solved it based on the PDP solver, right? Where you have one time derivative and one space derivative. So for such equations you can use your PDP solver, which are 1D problems, right? So this is best for 1D spatial problem and easier to start with, where you have to first write your system in this equation form and then provide PD function, boundary condition function, initial condition function to solve it, to your PDP solver. Then you have PDP toolbox, which is a specifically designed PD solver, which is GUI based, okay, where you can solve the 2D and 3D problems, right? So here you can put more than one variable in your system and try to and see how they evolve. You can provide various boundary condition, etc. So we will see this PD toolbox in the later part. First, what I will do, we will try to refresh our memory with the PDPE solver, where we will solve one-dimensional heat transfer problem through this solver, and then move ahead with the two-dimensional heat transfer problem, right? So in the PDPE toolbox, the general method that has been used is finite element method. I will come to that part also, okay? So before starting, is Matlab open? Not this. Yeah. Okay. Right. So this is the last week class where we had discretized our two-dimensional film into multiple grid points, and every grid point we computed the second order derivative with the finite difference method, and then moved ahead in the time to find the next value, right? So this is the one approach, the finite difference method, that we use to solve the two-dimensional heat transfer problem, right? And if you can run this, this is how our profile is changing with respect to time, okay? So this problem we already have done it in the last class, and I think I have a shared code with you, so you guys should be able to reproduce it anyway, right? And this is how your profile looked at the end, okay, near steady state, okay, where heat generation was at the end and the heat dissipation was at the boundary or the edges of your fin, okay? But this whole part was based on the numerical method, where we put our own code and did not rely on the any Matlab function, right? But now in the today's class, what we will do, we will solve the partial differential equation problems with the help of the Matlab, right? So first we have one direction heat transfer problem, where you have been given a rod of length L is equal to 1, which is initially kept at temperature 0. At T equal to 0, the left end is instantly heated up to U value of 1, while the right end is kept insulated, so that temperature change at your on the right hand side is 0. So how does the temperature evolve along the length of your rod? The equation that will be followed is given by the Fourier's law, right? So change in temperature is equal to thermal conductivity times second order partial derivative of your function or temperature, right? And the thermal conductivity or diffusivity value is given as 0.1, right? So let's try to code this problem here. So as you can see, this is actually one-dimensional partial differential equation, because you have spatial variation with respect to only x, and then you have time variation as a second derivative, right? So if I first search for PDPE option and go into the detailed documentation part of PDPE, so it said it solves a system of parabolic and elliptical PDEs with one spatial variable in x and one time variable, right? At least one equation must be parabolic. The scalar m represents the symmetricity of the problem, what kind of geometry you are in. The equations being solved are coded in PDE function. Initial value are coded in IC function. Boundary conditions are provided in the BC function, and the number of grid points you can provide through X mesh and T span, right? And here the detailed analogy was also given, that first you have to write your PDE in terms of this equation, and corresponding to that you have to find the value of M, find the value of C, F and S in your equation, right? Which then we supply as a function to our PDE problem. You also have to code your initial conditions, how it will look like, what are your boundary conditions, okay? So for that also you have to specifically follow the equations that has been given in the Matlab documentation and find all the other variables, right? So this was the whole idea, and you can then it will solve your function and provide you the variation in your function with respect to temperature as well as your space dimension, okay? So since I know I have to use the PDE solver, let's try to code this. This is one directional heat transfer problem, okay? Heat transfer 1D. So here what has been given to us, we have been given the length of a rod which is L is equal to 1, initial condition, boundary condition and the diffusivity, right? So let me write first, okay, let me close few tabs first, or else it won't work well. Yeah. This I think this also explained. Okay, here given parameters, so you have L is equal to 1, okay, your alpha is equal to 0.1. Till what time we have to simulate the problem has been not provided. So what we will do, we will consider some time instance t max is equal to let's say as of now I assume as 1. Okay, assumed, right? Creating data points for time and space variation. Okay, so what I will do, I will create x is equal to lean space, start from 0 to L. Let's say we have a 50 data points for the length part, then t is equal to lean space, I start with 0, go till t max, and let's say time 100 because I want to see the more variation in the time. Okay, let me suppress this outputs. Once this is done, right, now what we have to do is define the functions to represent PDEs and initial conditions boundary conditions of the system, right? So first, defining PDEs of a system. So when I want to define a PDE, what I have to do, sorry, once again this. So what we saw, we have to first relate our equation with respect to the code equation, find out what are the coefficient m, c, f and s, and then supply it into the PDE function. Okay, right? So here my equation looks like this, which is change in the temperature with respect to time is equal to alpha times du square by dx square, right? So if we relate it with this part, du by dt, coefficient c is 1, right, because here we have 1, and then x to the power minus m value here for us, we don't have any additional power of x, right? So then m is 0, so here it will become x to the power 0 is 1, x to the power 0 is 1. Okay, so m becomes 0, then your function of x du du by dx, so here that value is actually the first order derivative, so that will be du by dx only. Then s parameter, we don't have any additional term here, so s value will become 0, right? So I know my c is 1, f is du by dx, same as this case, and s is also 0, while m value is 0. So following the same analogy here, right? So let me create a function which returns CFS parameter in the Matlab. What is function which gives me CF and S parameter? I will write heat transfer one dimensional PDE. Okay, what value you have to provide? So that is also given, that it should be the function of xt u du by dx, right? So I can write it as xt, for time you can write capital T also, which is fine, dt by dx. Okay, my c value is 1, f value is nothing but dt by dt dx. Okay, and s value is 0. right? So this is my PD function. Now defining the initial condition for system. So for the initial condition you only need one output T0. I can write it as heat transfer 1D IC initial condition, function of x t capital D dt dx. What is my initial condition? So it has been given us in the statement that initially your rod is kept at 0 temperature, T equal to 0, right? At T, so all the U 0x value at time T equal to 0 are 0. So I can again write the function here, the initial value as, so you have to write it in just form of the x, okay. So u0 I can just directly write it as 0. Now this part is also not needed. It can be any function. So T0 is 0. Then defining the boundary conditions for system. I have function. Now for the boundary conditions you have to follow this equation and you provide PLQL PRQR, okay. This is how you write it. So PLQL PRQR, which is a function of your XL, UL, XR, UR and time, okay. So my PLUL PRUR is nothing but heat transfer one directional boundary condition, function of XL, TL, XR, TR and then time, okay. Now what is my PLUL? So boundary condition, one boundary says that so on the left hand side at x equal to 0 your temperature value is 1, u is equal to 1, right? And if I want to fit it into this equation, if I fit u equal to 1 in this equation, in this expression, for that my p value will be 0, my q value will be 1, my q value will be 0 since I don't have any function of x, t, u, right? So this will be 0. My PL will be whatever value I have at left condition, UL, temperature at left, minus 1 is equal to 0, right? Since my temperature value is 0, so I can write it as TL is equal to 1. So TL minus 1 is equal to 0. So my PL becomes TL minus 1, right? PL is equal to your TL minus 1, okay. This should be 0. Your QL is already 0, right? Now the right hand side condition says that right hand is kept insulated. So the first order differentiation of your temperature with respect to x is equal to 0. Now according to this equation I will have some function of du by dx, right? So my qxt is equal to 1, I don't have any multiplication, is equal to 0. So p is 0, q is 1. This will satisfy my du by dx is equal to 0 part, right? Correct? So here let me write PR is equal to 0, QR is equal to 1, Okay, so I have defined my functions. Now once we have defined it, calling a PDEPE solver to find the solution. So let me write solution is equal to PDEPE solver. What you have to provide? You have to provide the value of m value for our equation. We saw that it is 0 in this case. Then I have to call the PDE function, which is heat transfer 1D PDE. Then I have to call the initial conditions, right? So this is initial condition. You have to call the boundary conditions. Then what? You have to write X mass, T mass, okay, and then C. So let us run this part now. Clear all, close all, and CLC. So it has run without any error. I have to suppress output somewhere, T0. Anyway, and the solution. So we have discretized time into the 100 points and space into 50 points. So I have a solution. So row corresponds to time and column corresponds to your X variable. So initially all the temperature is 0, 0, 0, and then you at t equal to 0, you suddenly increase the temperature of your left boundary, right? So it should be at 1. Is it true? And then your for your right boundary, since it's insulated, the derivative will be 0. So the two consecutive values will be very closely related, right? Yeah, here. So at the end it will become almost constant. 8891, 8918, right? So the differentiation here will be 0. Now this is the plot, but I want to visually also see how it looks like. So for that, what we can do, you can take out this data, right? So my temperature is nothing but solution. So this becomes my temperature. Now what we do the surface plot of temperature. So this is how actually it looks like. I haven't labeled them yet, but you can see this is your space axis or x-axis and this is your time axis, okay? Let me do some beautification here. Let's provide the x label. This will be your time. Y label is your distance x, not distance, rather length, since it's a rod, length x, time t. Z label is your temperature part. So capital T. Okay, what else? Let me just quickly see through the reference part. Title is fine. Z label, surface xt, you can add x is t. Okay, this is different. So yeah, here, sorry, my x variable is time and My x variable is actually distance and y variable is time, and let's run it. So this is how it looks like. At t equal to 0, every value is 0, right? And at the next step you increase the temperature at the end, which is kept at 1 value, so the constant value of 1, and with time the heat transfer will happen and the temperature of the rod at the other point will also start increasing till some point where it reaches the steady state. You can see here it hasn't reached steady state yet, so it's still increasing if I look at from this direction, right? So for that, let's look the two-dimensional part, okay, and see how it looks like. So this is your first plot, plotting spatio temporal profile. Okay, now second I want to put is, let me call it as figure 1. Plotting 2D profile of t versus x at different time, right? So I can do plot. Now here in the temperature I know the various values, right? So you know what is the variation in x versus t. Let's say I start with t equal to 0. What is the value at, then again x t at, what is the value at 5th time point, value at tenth data point, then x comma t 25, x comma t 50, and final value which is end value. You can also put a line style. Okay, so let me put a common line style everywhere except the end part so that we can differentiate it. You can add line width. Let me add line width of 2 or 3 maybe. Your x label is length, y label is temperature, your legends. So here we have different time instances, right? So one is t is equal to 0, I can use disp command, right? Just a minute. So this is x label, y label, figure, let me call it second. Let me just see the command here. I have written it manually. Anyway, we can do this also. So you can write 1 is t is equal to 0, then your 5th data point is 004, let's write the value rather than doing this. Percent f 0.4f. Percent 0.4f. How many data points we have? 1, 2, 3, 4, 5 and 6 plots. 1, 2, 3, 4, 5th and 6th, and the value we write it as tau comma 5. I just forgotten the command, so I'm just checking whether it will work or not. Sorry for that. 5, 10, then you have 25, 50 and the end value. Okay, let's see if it works. Yeah, I got an error. Oh, it should start with 1. Yeah, no, it's not working. Okay, yeah, but this is how your profile will look like. This is at t equal to 0. This is t is equal to a 5th step, 10th step, 25, 50 and at 100 step, right? So eventually all the values will become 1, since temperature is fixed here and all the heat is being transferred and the other end is insulated, so there is no further point of heat transfer, so your temperature will keep on increasing till there is no further gradient, right? Just figure out the legend part. I have forgotten the command, so this you do it, or you can just manually add legends for all the part, right? I think it was display command, I forgot, but anyway, right? So this was the first part where you can see the evaluation of your temperature profile in your rod with time, right? So this was one directional spatiotemporal problem, right? So for that, since we know that PDP solver is useful, we relied on that part. Now let us move forward with the second example, which is on two directional heat transfer problem. And here what we have been asked is, please find the steady state temperature on a circular disc. The top half of the boundary is held at 100 degrees centigrade and the bottom half at 0 degrees centigrade, and that's it. We don't have any other information provided, right? So this is kind of a practice problem to see what will happen when in the PD modeler part. So let's jump right into that. Before that, just give me a minute break. Okay. So now we will move forward with the PDE modeler. And now before I start with this GUI based solver, let me just give you a slight disclaimer that I have been also introduced to this PDE solver recently, in the sense that I have not used this GUI based PDE solver previously. So my knowledge about this is also limited. I have tried to look at some examples and understand this into more detail, right? But still I'm figuring it out. So in this class, kind of what we will be doing is discussing this solver and how we can utilize it to solve various problems which are beneficial to us. Okay, so it will be kind of understanding the solver for you also, for as well as me also, right? So this is how I have taken some problems also. These are very basic problems where we will try to understand what each parameter means here, right? So the problem is clear, and that we have been asked that you have a circular disc. Top half is subjected to temperature of 100 degrees centigrade and bottom half at 0 degrees centigrade, and just find out what is the change in the temperature. Now for the PDE modeler, so you have this PDE toolbox available in Matlab, which is a GUI based, graphical user interface based solver, right? So if I search help PDE tool, so PDE tool is a graphical user interface. Here it's written PDE tool is not recommended, use PDE modeler instead. So it's like previous notation which was used, now it is PDE modeler, right? But still if I call the PDE tool, it should work. Yes. So essentially it opens the PDE modeler part, right? So the name has been changed recently. Okay, so it's a graphical user interface. If I just call PDE tool or PDE modeler, it will open this GUI based interface, right? If I write PDE modeler also, same thing will happen. Now the interface of this PDE modeler is that you have given this 2D geometric plane, right, where you can draw various shape of your system. You provide the PDE to represent your system, you provide the boundary conditions, etc. Obviously the detailed run through of this has been already provided in the SIRS lecture, right, the NPTEL video lecture that you have seen, but still let's explore them and see what all options we have. So if I click on this rectangle and draw it, it creates some rectangle. If we double click on it, you can provide the dimension of this rectangle, what should be its length, width, where should it start, the origin, etc. Right? So let's say I just want to initially I just want to understand what is happening. So let me do start with 0 0. Width I want to keep 0 to 1, and height should be 0.01. Okay, let me create this kind of plot. So I am kind of creating a 2D rod here. Okay, let's see. Then you have a different options here. So this option of grid spacing, these are basically for your this visual toolbar representation, right? So if I turn on the grid, it will show the grid lines here. You can adjust the grid spacing, etc. So this is for your purpose only, and it does not relate to the region that you have provided. Okay, now the axis limit also. So here what I prefer is rather than providing the axis range or x-axis and y-axis range or zooming in or zooming out, just do a auto click so that whatever geometry you have, you only see that part. Okay, this is how the way I preferred it. Okay, you can zoom it, zoom out, etc. You can draw further to this element also, as has been shown in the class, that you can add additional geometry, you can subtract a geometry. Okay, then to provide the boundary condition of your problem, you have to go into the boundary mode. when you go into the boundary mode, actually this is very small, so let me change the axis limit anyway. 0. .3, this to minus 0.3 and apply. Close, right? So this is my 2D rod kind of a thing. And if you go into the boundary, click on the boundary mode, only the extreme edge of your geometry will be seen, right? And when I do show edge labels, I can see the labels of this edges. So I have 4 edges, right? 4 sides of my rectangle. So 1, 2, 3, 4. And clicking on any of it, it will open your toolbox to put the boundary condition. Now in the boundary condition, as I was discussing, the boundary condition we can further differentiate into 2 types, right? One is your fixed value of your function, so that is Dirac boundary condition, and second is the Newman boundary condition, which is based on the derivative of your variable, right? So here you have 2 options. One is the derivative based and one which is only the function value based, right? So these 2 options are there. Then you can provide the individual boundary conditions by clicking on all the edges, or you can just directly put the value here. Okay, let me try to put some boundary conditions. So let's say if I am simulating the 2D rod, first I will show you, I will just explore this as a normal tool, and then we will solve the problems which has been given into the notes, right? So the left extreme, I cannot click it. This is actually very small. Edit options. Yeah, here. So the left edge. Zoom. Boundary mode. Yeah. So left value was subjected to HU is equal to R. Yeah, one more thing here. So if you will just use the default value, so here you have various applications of PD solvers available already. So if you select a specific application, let's say here the heat transfer part, all of your boundary condition and PD equation will be converted in terms of the your specific problem, right? So here now you can see G and Q as written in terms of the heat flux, heat transfer coefficient. This is the weight and temperature value, etc., right? If I keep it as a generic scalar value and I click on the boundary conditions, there is no description, right? So what does Matlab does is, based on your application, it provides you the equation in that particular coefficients. So if I go here in the PD part and try to provide what is my PD equation, so what will be its variable, you can see it provides me the generic equation, like for elliptical this kind of equation, for parabolic this kind of equation, right? But if I just change it to the heat transfer problem and then I look at the PD, so it changes your equation to represent your particular problem, right? So this is how it looks like. Now let me try to see if I can simulate that 2D that 1D rod problem, but essentially with a very fine thickness, fine thickness, very small thickness, right? So here my temperature value I know on the left hand side is 1, okay, T is equal to 1. Right hand side I know the derivative of my function should be 0, okay. So for that heat transfer coefficient Q value is 0, G value is 0, so that will be gradient of temperature will be 0, right? So this is correct. Similarly, for part 3, I want that gradient is 0. I am considering it insulated at all directions, so there is this only one directional flow. Okay. Let me go to PDE solver. Now here the equation selection part. So this is an important aspect. What we know here is this, that our equation looks like in the previous example 1D problem. My equation looked like this: du by dt is equal to alpha del square u by del x square, right? Where I knew the value of alpha. Let's consider time variation as of now as 0. Then so I don't have any heat generation, so Q should be 0, heat source is 0 in this equation. My H value, there is no convective heat transfer, so that is also 0. I don't have any external temperature happening, so this is also 0. Now divergent of K gradient is equal to 0. K value I know, alpha value I am putting it as 2, right, in this equation. Du by dt I am considering 0, so that means I am considering what will be the profile at a steady state. So it actually should be same value for all, right? So if I do OK and try to solve it, so for solver, solve PDE, this is how it's giving me the profile. So essentially this value is 0 across all the points, right? Go to the solve part and select the parameters, not here, sorry. Go to the plot parts and select the parameters. Here you can select the contours, you can perform the height value, arrow value, etc. to see the change. Okay, so let's see how that change looks like. So this essentially shows let me remove this and just do this. So since the values are almost constant, it's 1 1 1, it's showing the directions, but actually it won't be a direction. Maybe this is not a good example to show the arrow values, right? I will show you at the end. Okay, let it be this way as of now. What you can do here is go to the boundary mode. So here what I have kept 1 and 3 as a constant value, insulated value, and second also as a insulated, right? So at the steady state all the temperature value will be 1, right? What we saw in our previous example in the one dimensional rod, although it was one dimensional, you can see the temperature profile was increasing with time, and at t is equal to infinity you will get a constant value, right? So same thing is happening here. So now let's try to, what we do, we will keep the edges as insulated. Your left part is a heat source and right part I will consider it heat sink, right? So that I will keep it at t equal to 0. So then there will be some gradient, okay? And then we will be able to see the heat transfer direction. So for the right hand side edge, let me change the boundary condition. Boundary mode. So boundary mode. Okay, instead of the Newman's condition, let me provide the direct condition where I want to keep HT is equal to 0, like temperature value is equal to 0 on the right hand side. All the other conditions remain same. Here this 2 arrow shows you the grid data points that will be selected for your problem, right? You can provide multiple grid data points also. This will do the final grid and compute the values at each point, right? For the simple problem it won't matter much. Now let's solve this PDE, right? So this is how it looks like. Your direction is changing, so it's high, it's going from 1 to 0. So heat transfer is happening from your left point to right data point, okay? So this is how your profile looks like. You can further do in the plot parameter. let me just look at the contour only and plot it. So this is how temperature variation looks like. If I want to see the heat flux, or let me just look at the heat flux from left to right, how it will look like, and plot it. So this is how heat flux will look like. On the left hand side your heat flux is less, on the center it's more, and the right hand side is less, although it's constant for both the ends. Okay. Anyway, so this is how your problem looks like. So saying one directional heat rod problem, I just consider the slide thickness and consider both the edges as insulated, so you can try and see what will happen at this steady state, right? So since here we don't have the time part, we are basically looking at the variation in your function, or variation in your whatever variable you have considered with respect to x and y direction only, right? So what you are looking at is the steady state condition. Now what has been asked to us is about finding the steady state temperature in the circular disk. Okay, so let's simulate that. Let me close this. No, I don't want to save. Okay. Let me call a PD modeler again. No, we have been asked that we have a circular disk. Okay, nothing else has been specified. First I have to make sure that it's a circular disk. So for that, its center should be at 0 0, not 0 0, but at the same value, and then center could be at any point, but the dimensions, the radius should be the same, A semi-axis and B semi-axis. So let me select half a radius for this point, for this circle, right? So this is how your circle will look like. Now let me see what are the boundary conditions I can provide. So if I select the boundary mode and click on the show edge label, I can see 1 2 3 4 two conditions, like four edges. Okay, so 4 boundary condition I can provide. And what has been said to us, that top half of the boundary is held at 100 degrees centigrade and bottom half at 0. Okay, so 3 and 4 are at 100, 1 and 2 are at 0. So if I click on them, so it's top half is at 100, bottom half, sorry, again this is top half, so this is 0, bottom half is already at 0, right? This is already at 0. Now going into the PDE part and selecting the PDE specification. So now here we don't have any information provided, but again, like the previous case, I will consider it as a steady state heat transfer problem. Okay, so for that we have only variation in the x and y, right? So you have divergence of C, gradient U, this additional parameter are 0. Okay, so AU 0, F is equal to 0. Your coefficient, I am considering alpha value as of now as 1, and let's see what happens. Okay, so you solve this PD and see how your profile looks like. Okay, since obviously it's intuitive that your top edge is at 100, bottom is at 0, so there will be heat transfer, and in between you will get the temperature gradient, right? Now here, if I do in the plot parameter, if I want to see the directions, which will be the gradient of U, okay, this is how it will look like. So your temperature is high at this point, low at this point. So it's going from up to down. So gradient is in this direction, right, from top to bottom, for in a circular motion at the edges. Okay, so this is how your gradients look like. You can plot it in a 3D kind of a plot also to see how this gradient look like. Okay, so this is how the value is. Your top value at 100, top part value, bottom part at 0, and this gradient shows the transformation. So this arrow shows in which direction your heat will be going. Okay, I hope you are able to understand it. You can also look at, instead of the property itself, absolute value of gradient, absolute value into the uh, c is a constant in your multiplication part, right? What will be that value? So if I look at the absolute value and plot it, sorry, not this, remove the 3D part, remove the arrow, and just look at the absolute value of the gradient, right? So major gradient is at this two extreme edges, right? Why? Because this is the boundary part. Above it you have 100 degrees centigrade temperature and below is a 0. So this portion, these two edges will be the extreme heat transfer point, right? So that at this point your temperature gradient will be the maximum, right? So that's why your gradient values are maximum. For the other parts, your gradient values, the minimum will be at the center, because here you will observe the gradual changes, right? This is the absolute value. Let me look at the absolute C in the grade. Okay, this doesn't change anything, because in your PD, C is your coefficient part, right? Let's say instead of 2, I provide the 3 and solve it. What happens? And I'm just trying to see what this parameter does. Okay, so essentially it's what is happening is your gradient has increased, right? So C, for our equation, if you try to relate it with the 1D heat transfer problem, it will kind of correspond to your thermal conductivity. So if your thermal conductivity is high, your gradient is high, right? So faster heat transfer is happening at this particular data points. Okay, now if I want to know the value of this data points, I can export the solution. Okay, export the variable u. If you press the OK, and if you go into the your Matlab window, in the workspace you will find the variable u, right? Now the change in the u is given from 100 to 0, but for me, how to understand this is, it's difficult, right? If I just type u, it's a vector, but how to understand this vector? So for that, what you can do is export mesh PET. So basically you have to export other parameters also of your mesh grid points, right? Then only you will be able to understand what is the value of where which value corresponds to. Here, solution mesh show triangle labels. Yeah, so basically you have this many data points and you have to know what is the value of this. What you have been given is the value of each of these nodes through your PDE solver, right? So this U matrix or U vector of 146 into 1 data point is nothing but this 160 data points where your temperature value has been given. Okay, now we have to find a better representation to take out this data point, which I am unaware of. PD specification, draw, option, application, edit. let's look at the help module for this part and see if we can find out how to export the solution. If not, then I will find it out for the next class and let you know. Okay. Here you have been given some examples also, like heat transfer in the block of cavity, how the heat transfer is happening. You can follow these examples also, right? This doesn't provide me how to solve it, solve 2D equations. Okay, let's leave it for as of now, since we are running out of time. Okay, what I will do, I will find out how to save this data point in the next class, so that we can extract out which u value correspond to which mesh grid point. Okay, and we'll let you know, we'll update you about that. Okay, so this was the first part. It was just to show you how we can solve, we can use this PDE solver. Now here, let's say if I want to save this data point, so when I do save as, you can save as a Matlab file, which is a, let's say, circular disk, and it saves as a .m file in the Matlab, right? And when I click on it, so it does nothing, but it's like all the whatever changes we did in the PDE modeler, okay, all of that has been written in form of the command prompt here, right? So let's say when you want to when you want to solve your PDE equations without the help of relying on GUI, and you want to create your own commands, so for that what you have to do is you have to understand all of this PDE tool options, right? So this is like PDE tool option, which creates your axis limit, which creates your tick marks, it creates your objects, provides the boundary condition values, okay, provides your equation 1 data points, etc, etc. So all of that thing is done. So when I run this, what I will get is a PDE modeler. It will open and it will give me the same exact things that I have done, right? So once you solve your problem in PDE modeler, save it as a .m file, which will give you all the commands. You can understand them. You can look into the documentation of PDE toolbox to further see how you can create a circle or rectangle with the help of this PDE toolbox, so that if you don't want to write your commands, right, in that case it will be, if you don't want to rely on GUI, it will be useful. Now where will be that case? So if you recall the previous class where we had done the 2D fin problem, in that class we were doing the time evaluation of the temperature profiles, right? So with the time, the base of the fin, it was subjected to the heat generation, right? And that heat generation was time dependent. Because of that, the temperature profile was changing at the bottom, and obviously because of the conduction and the convection, the overall temperature profile of your fin was changing, right? So now let's say you want to automate this process. So in that part we relied on the finite element method and solved the entire problem. But same problem if I want to solve with the help of the PDE modeler in my system, right? So in that case you can run one for loop where your time is changing from 0 to your desired value or the steady state value, okay? For each time point you take out what is the corresponding value of q, okay? So we had that equation, q is equal to I think that it was 10 to the power 4 into the exponential term of the time, right? So you know what is the value of q. That q value will go into your data point, that q value will go into your boundary conditions, right? And then you solve, then you call this PDE modeler put all the conditions, solve it, extract out the data. Again you move for the second time, you compute the new q value, put all the boundary conditions again, and then find out the solution, right? So in such cases, when you move forward with the time, you can use this PD modeler, right? So where you are changing also the boundary conditions, right? So here the equation parameters are set, the boundary condition data are set, right? So the 100 and 0. Let's say if it was the gradient part, it will show the some other values, right? And then you can put some variables which will change this boundary condition values. Okay, this was this previous example, right? So here you see the heat generation part is this part. It is time dependent. Okay, you compute what is the heat generation for that particular time, put it into the boundary condition and solve it. So this is how also you can use a PD modeler to solve your time variation. Okay, I haven't done it, I'm suggesting it because this is how I'm think it will work. I will obviously try it out and let you know, but you can check it on your own whether we are able to do it or not. Okay, in the next class, if I am able to do it, I will let you know that we can use the time loop and change the boundary condition in the loop and are able to solve it or not. Okay, now let's move forward with the next question, which is the two directional heat transfer problem. Okay, now problem 3 and 4 both are the two directional heat problems, where you have this rectangular board is given, or the square board with different boundary conditions, and you have to find the steady state temperature. Now before that, I just wanted to check one thing here, which is on this circular disc part. So as you know, we can also create the holes in this part, right? So let me go into the draw mode. Let's add one more circle. Okay, here I want to do it 0, 0, 0.25, 0.25. Okay, my system will be E1 minus E2. Okay, go to the boundary mode. Yeah, here, yes, boundary and the show edge label. Okay, now here what I have done is I have created one outer circle, one inner circle, subtracted the inner circle from the outer circle, so you are left with this kind of a part, right? If you go into the PD mode, this is how it's a circular thing, right? So you can imagine it as a cross sectional area of your pipe, right? Where you have outer side is subjected to the hot temperature and inside is subjected to the cold temperature. And I want to see, basically I want to simulate whether I can see the heat transfer profile across the cross section area of a cylindrical tube in a heat exchanger or not, right? So let's try to simulate that. The problem 3 and 4 we can solve it later also, right? So this is how my profile looks like. Let me go into the boundary mode. Now I have to provide the boundary conditions. Okay, so first let's start with a basic thing that my outside fluid is at some constant temperature. Okay, so let's put all the boundary conditions here, that my outside fluid, let's consider it at 70 degrees centigrade. Okay, 70 here, 70 here, 70 here, and come on, 70 here. Okay, now with the inside fluid, let's consider the cold side at 30 degrees centigrade. Okay, not too high. 30 degree centigrade, 30 degree, and this one also at a 30 degree centigrade. Okay, now let me go into the PD modeler, PD specification. Again, I am considering a steady state part, right? So that's why my A and F parameter I am keeping at 0. Let's consider C value as a 2 only as of now. Okay, right? If I do the heat transfer equation and see the PD, KQ0. Oh, I have to provide it again. Sorry, my mistake. 70, 70, 70, okay. Now let's solve this. Solve PD. Yeah. So this is how your profile looks like. Okay. So basically, what we tried to do here was consider a scenario, where we are looking at the heat exchange happening in a shell and tube heat exchanger. So you consider a tube in your shell and tube heat exchanger where outside fluid is a hot fluid, inside fluid is a cold fluid, right? Outside fluid is at 70 degree centigrade and inside one is at 30 degree centigrade. So this is how your profile will look like. So how the conductive heat transfer will happen from this place to this place, like from outside to inside. Okay, you can further look into the different parameters. So let's look at the temperature gradient arrows, okay, and the 3D plot. See, this is how it looks like. So your heat is being transferred from outside to inside, right? This is how it looks. If you will look at the 3D aspect, yeah. So this is how your 3D temperature profile looks like. So your heat is going, it's like outside fluid which is at 70 degree centigrade, and then that heat is being transferred based on your thermal conductivity value to your inside fluid at 30 degree centigrade, right? Now the rate at which will be transferred this heat will depend on your alpha value, right? So here in this case, the K value I had kept it as 1. So let's say if I keep it as 3, okay, so in that case what will happen, right? I think the gradient will go down. Let's see. Solve PD. Okay, yeah. So okay, basically we are getting the faster gradient. Solve again. I want to see plot parameters instead of temperature. I want to see the temperature gradient. Let's not put a 3D height and then see. Okay. So temperature gradient is much higher on the inside part than the outside part when I am increasing the k value. Okay, so inside the gradient is going 200, outside is 130. Let's see if my material has a different property. For PDE, instead of k is equal to 3, let me provide k is equal to 10 and see what is happening. Okay, so gradient has increased slightly. So previously it was 190, now it's 200 at the center and 130 obviously outside, right? For the one value, I think it was the low. PD specification, let's say 0.5, I keep it half and solve it. No, actually gradient is not much affected, sorry. Anyway, but my point was that you can also simulate such sort of a scenario, right? The 3D view looks much better about the change in the temperature, right? So this is how your change will happen within the cross-sectional area of your cylinder, right? So something which you cannot see in the real life, you can visualize the transition that is happening inside this toolbox, right? With the help of this toolbox, you can see how this variation of the temperature is occurring, right? So that was one example. Now further also you can again, this is just my thought process, that what you can do is you can try to incorporate defects into your this cylindrical geometry, right? So in the PD toolbox you can also draw it, right? So what happens if you make your edges inside your heat transfer area, the cylinder rough, what will happen, what kind of heat transfer you will get at that particular point. Apart from that, what you can do, you can put a various gradient conditions also to see how the way the temperature profile will evolve in the cylindrical conditions. Okay, so again, so the goal here is that you should be able to understand the solver and try to apply it to your problem. Okay, that problem could be anything, right? So there is no specific example manual present for all different case scenario. This is just what I have thought as of now. Similarly, you can think about your problem and try to fit it into this solver, whether you are able to compute such profiles or not. Okay, so that will depend upon you also. Okay? Right? Now let's look at next example, which is also kind of a similar to the two-direction heat transfer part, where you have a metal plate of 1 cross 1 meter diameter, 1 cross 1 meter length, which is placed such that the four edges are kept at different temperature as shown here. The steady state conditions are given by the Laplace equations. Okay, so del square t lx by del square t by del x square plus del square t by del y square is equal to 0. And as we saw previously, the Laplace equation follows the elliptical type, right, where your b square minus 4ac is equal to 0, right? So a and c here are 1, b is 0, so minus 4 is less than 0, so you are elliptic, you can use the elliptical equation, right? So find the correct temperature distribution in the plot. Let's try to simulate this also. Here let me call a PDU modeler, right? Put geometry, this is a square geometry, right? So edge starts from the 0, both the part 0, it goes to 1, 1. Okay, you can name it also, I haven't square. Yeah, axis limit, let's keep it at auto. This is how it looks like. Boundary, go to the boundary mode, show the edge label. Just give me a minute. Okay, so let's provide the boundary condition. So what are the boundary condition? That your left edge is kept at 30 degrees centigrade, right edge is insulated, so your gradient is 0, top edge is at 40 degrees centigrade, bottom edge is at 20 degrees centigrade. Okay, let me change my problem to the heat transfer problem so that I am more familiar with the coefficient. My left temperature value is 30 degrees centigrade, right? 20, 30, 40. So this is at 30 degrees centigrade. Bottom one is at 20. Top one is 40. And the right hand side, I have the derivative based Newman condition. So here my gradient is 0, right? So Q value is 0, G value will define what is the value of my gradient T into the all multiplication bar. So heat flux at the end will be 0 since it's insulated, so that's why G is equal to 0, right? Now go to the PDE solver. What kind of equation you will have? So this becomes your elliptical equation. Why elliptical? Because here we have been shown that it's a steady state part, and you have been given the Laplace equation, del square t by del x square plus del square t by del y square is equal to 0. Okay, so this becomes your elliptical part. Your k value has been not specified here, right? Okay, we can consider it as 1, right? Q value, there is no heat source or sink, so Q value is 0. There is no convective heat transfer, and then no external temperature, so everything I'm keeping at 0, 0, 0, right? Once you do that, all the boundary conditions are defined, your solver conditions are defined, then you can solve this PDE, right? So this is how your profile looks like. Now I know it doesn't strike much because it's a hypothetical problem, right? Your bottom edge is at 20 degrees centigrade, top one is at 40, left one is at 30, and the right one is insulated, so here the gradient is 0. You can try and play around with the boundary condition to see what happens. So basically you can look for the various scenarios of the heat transfer, right? So if I think about it, this could be a connection between some two metallic plates in your conduction experiment, right? Where let's say your top and where your one edge is insulated, other two edges are, let's say, subjected to some cooling condition, right? So here this one is at 30, so instead of 30, let me put the left edge at higher temperature of 50 degrees centigrade. Okay, 50, and both the top and bottom part, let me make them at some low temperature value, or let's say cooling water temperature 25 here also. Okay, and now let's see what kind of profile I get. Okay, so this is a heat transfer that is happening. Okay, now again this is kind of similar to what we did in the fin part, right? Where you have a heat coming from the bottom edge and it is being transferred into all the other areas, right? Now the same problem, the fin heat transfer problem, right? You can try to solve it here also by changing the boundary condition. Okay, let's go again into the boundary mode. So if I consider this as a heat source, I have considered this part insulated and this two part at a constant temperature, but instead let's try and see what happens if it is subjected to some ambient air condition, right? So either you provide a heat flux. Okay, so heat flux I don't know, I don't have any value, right? But I can provide the heat transfer coefficient, maybe it's subjected to some ambient air condition. So let me provide the value of heat transfer coefficient 50. Same for the bottom part also, there is no heat flux, additional heat flux, but the heat transfer is happening with the surrounding. for 2. Same I will do for this edge also. G is 0, but heat transfer coefficient I am putting at 50. In the PDE solver, in the elliptical part, external temperature, let's keep it as 25 and H value as 50, and then see what happens. Okay, so now I can see the gradient where my external temperature is going till 0. This should not happen. This is at 50 degrees centigrade. 555 by 0. Let's look at the boundary condition again. My heat flux is 0. Gradient of T is equal to H into T. Why will this happen? 50. PDE specification, external temperature, let's say 25. I'm not sure about the 0 value here. Let me see what I can do. Boundary mode. Nk gradient of T with respect to Q1T. So T minus T0 by dt is equal to 1. PD specification. T external minus T. Zero. Still it goes to 0. Okay. Fix the extra. Now, the same is happening. Not sure about the boundary condition equation here. Let me work out on that. So some of the question I will try to answer in the next class. One is obviously how to store the 2D grid data points and how to take out which data points corresponds to the which value in your 2D plot. Okay, that is the one aspect. Second aspect about solving the heat transfer fin problem with time. So what happens if I want to include the time parameter, the variation in the time, to see how the temperature profile will evolve. Okay, and this third aspect, what about this fin example, right? So basically here what you have to do, like if you want to understand more, go into the documentation part, see the example provided in the Matlab toolbox, and try to relate the equations, right? That I haven't done it, because of that also this error is coming. Okay, so try to see and find out what equation represents which parameter, and if you want to put it into in the Matlab format, how you can convert your equation into the Matlab format, right? And then you will be able to solve it. Okay, apart from that, you have this problem 4 also, but since we are out of time, I am not solving it. This is essentially same as the problem number 3. Instead you have just some different conditions, right? So insulated boundary, same as the previous one. So your gradient will be 0. This is at constant temperature, and at this 2 points you will have a heat transfer. right? So this point is at constant heat flux, so you will have the Newman boundary condition, but your Q value will be there. You can put it here, okay. In this part your H value will be there, and the infinity temperature, the external temperature is given, which is at 30 degree centigrade, and the K value and the parameters for the geometry are also provided, right? So use a PD toolbox, find the steady state temperature distribution, okay, and what are the steady state temperature values. So this was it from my end for today's class, okay. See you guys in the next class, where we will further discuss about this PDE solvers and other problems, right? Thank you.